In this video, we'll talk about all the terms, alright, that we have been talking about in the previous all the videos, alright. So in order for you to understand in a more overall type of view, the sensitivity function 1 over 1 plus CP, alright, is this one. This one is the, if you were to multiply by a controller, alright, then you become SU, which is a control sensitivity function. Alright, so S when multiplied with C, in fact we can also put it as P naught, S naught. Alright, and therefore what we have is the control sensitivity function. You can do that. Alright, and if you were to divide by S, so 1 divided by S, so currently this is S, so 1 divided by S we will get a SM. We call this the vector margin or the modulus margin. Alright, and this is 1 plus CP, because 1 divided by this whole thing is simply 1 plus CP. That's just math. Same thing as for T. CP 1 over 1 plus CP is equals to T itself. It can also be T naught when your P is P naught. Alright, it's just the terms. And if you were to multiply with a filter F, if you still remember from the block diagram, where you have all the disturbance and the noise over here, alright, and this is your reference signal, and when you reference signal input, there will be a certain filter. So this filter actually cleans some of the reference input, and therefore this F is just some constant number. It can be a function, but we just keep it as a filter. Alright, and some numbers is equals to y over r, where this whole relationship relates back to this one. Alright, if you still remember that just now that block diagram, if I were to carve out disturbance and noise, I'll just analyze in terms of this whole feedback system. With regards to the reference signal, what I have is FR TFR. Alright, is equals to your output Y. Alright, so in other words, this is FR, so far so good, and this whole loop itself is CP naught 1 plus CP naught, which is also equals to T naught. Alright, so T naught times FR, what you have is over here, and this represents your output over here. Because output is a response, and therefore we call this whole stuff the command response. Alright, call this whole thing the command response. And if it's, as I say, if it's P naught, then this is T naught, and then we'll call this also command response. Alright. Now, if you were to 1 divided by T, where we know that this is T, if I were to 1 divided by this thing, I'm just flipping around. Alright, I'm just flipping around. And what I have is 1 plus CP over CP. We can also have P naught over here and T naught over here. Same thing. And the outcome is a complementary vector margin. You still remember this is the Nyquist plot. Alright, we call this CP. This is the loop. The whole curvature is CP. Alright, and the distance between -1 and CP is simply 1 plus CP, which is our vector margin over here, SM. Alright, so therefore, in an attempt to actually explain complementary vector margin, what I would believe is it's a ratio between your vector margin, alright, divided by your curve over here. Or it's just a ratio between them, and the meaning itself I really don't know. We want both of them to be large. Alright, we know that vector margin must be large because you'll be further away from -1. But what about this very abstract form? Alright, we don't want CP because this is a ratio between the distance from -1 to the loop divided by its own loop. Alright, divided by its size. If it's a very big size, alright, this whole thing would somewhat equals to 1, because if 1 plus 1000, if CP is such of a big number, huge number, what we have is only 1. Alright, so this means that you're actually at 1 now, and therefore you are unstable. Alright, as for CP, alright, if its CP is small, maybe 0.05 for example, then what do I have? I will have 21. Alright, and this 21 is much larger than just now what we have done, the 1 value, right? And therefore this also means if the CP is 0.05, this means that it's actually very small. Alright, which is somewhat over here. Alright, so it's actually far away from the -1. So this is somewhat of the meaning of the ratio of that, if I didn't explain in the previous videos. Alright, therefore all the margins, if you see a margin over here, this means that everything must be large. Alright, that's just that meaning. Alright, even for gain margin and phase margin. This is somewhat your starter kit. Alright, when you buy something, you have a starter kit. Alright, then now you can mix and match. Alright, we can take this control sensitivity function. I'll just copy and paste it over here and multiply by a p0. Alright, so this is our sensitivity function over here, and we multiply by p0. What you have is t0, which is this one. Alright, which is this one, which is cp1 plus cp. So I'll just simply copy and I'll just also paste it over here. So our complement control sensitivity function times the plant will give us our t. Alright, given that this is the p0 itself. Alright, and this is just another way to represent your complementary sensitivity function t. Alright, and the purpose itself is to actually talk about how this input, if you still remember, SU relates back to this part over here. It's just going into the plant. Alright, it's just going into the plant. Alright, it's an input to the plant for some sort of a reason. Therefore, by measuring this thing and input into the plant, you'll know that what is the outcome of the T0. And we do not want our T0 to be very high, right? If the T0 is very high, this means that your plant cannot take it. Normally in the plant capacity concept, T0 is actually somewhat of a measurement to actually set our boundary. Alright, if T0 is larger than 0.8, then it's unstable. The whole plant will fail, something of that meaning. So therefore, we represent in terms of T0 to that extent. Alright, now this control sensitivity function is like a magic. It can also be rewritten as approximately 1 over p0. Alright, how do we do this? Alright, is that this thing over here, alright, if you were to cancel it off, what you have is simply going back to SU. If I were to paste it, copy, and let's paste it over here. Alright, it's exactly the same. You can just compare and look. Alright, just C times 1 plus CP. Alright, over 1 plus CP, sorry. And therefore, so I simply rewrite this in terms of that and that. Alright, so this is simply T0 also, if you can somewhat see. Alright, it's over here. Alright, so if such a case that happens, then if let's say CP0 is a large number, alright, for this case, the CP0 is a super large number, like 1000, 1 plus 1000, what you have is approximately to 1. Alright, so 1 times, so this whole thing will become 1 times 1 over p0. It will give us our control sensitivity function, which also proves that this is approximately there. And this is somewhat also used for calculating, alright, your plant capacity in terms of its plant itself, because the plant itself has a certain transfer function, alright, its own stuffs over here, and then talks about the right hand pole zeros and things like that, and how does the bandwidth move as your system becomes a little bit more wear and tear, such that it creates more gain and actually shift your bandwidth to a more dangerous area, or maybe a shorter area such that your operating frequency is being limited. Alright, some sort of the meaning in there. Alright, watch the video. And the lastly is CP is known as CP0 also. It depends on whether you're talking about a brand new plant, and after a certain while, maybe 10 seconds, or maybe another second, or maybe another year or whatever, this will become P, or maybe P1, P2, P3. Normally that's how you deal with the time zone. Alright, but we'll not go to there. But CP, you can write CP as L. Alright, it's in fact CP and L are the same thing, just a representation of the loop gain. And we call this loop gain simply the curve of the Nyquist plot. Alright, this plot itself is the Nyquist plot, and we call this the loop gain. Alright, for example, if the loop gain now is L0, or we can know that it's CP0 because CP0 is equals to L0 itself. Alright, and a long time, a long certain period, the system may actually perturb towards this side. And you may not know. Okay, it is something that you may not know. You may not know means that you're talking about loop uncertainty. Right, when talking about loop uncertainty, you got somewhat use the Doyle's criterion to actually create a boundary such that this loop uncertainty is within the boundary itself. Alright, if we purposely will want to amplify this certain loop, alright, such that this loop can become this one, we purposely make it like this, and we can call this the loop shaping, because we purposely shape it to a new loop such that it is something that is still within our bounded system. Alright, so this bounded means that the blue color one, if you happen that you have a certain plot that is exceeding this blue color line, this means you're unstable already. So this is by the mean of the bounded, and therefore Cp0, as you know, if Cp is equals to L, then therefore the rest of this can be all written as 1 plus L, 1 plus L, type of thing, like this. Alright, and you can all written like this, and then if it's L naught, then you just write naught, and these other things. I think you should most likely know. And therefore this is it for the description of all the terms that is within the feedback control stuffs. See you soon.